Thanks, Lumo. And it's great to be here at this conference and particularly to celebrate Kenji's work. Of course, this talk, the kind of categories are going to play a very central role. Yeah, so what's the kind of thesis here is that there's some kind of equivalence of two things. But what's kind of really hiding behind this short title, what is to be kind of really going on? What am I doing? So the setting is I have some real domain, and in fact, I'm going to stay kind of two real dimensional. I want it to be a real surface. Although kind of in principle, there's anything stopping you from going to higher dimensions. Just things will be more complicated, of course, with some grading. So to make the category C-graded. And yeah, so now starting from this sort of data, there's going to be two associative algebra associated to it. So on one hand, the first step is to consider the Fukaya category. And since you will, I can consider it over any field. In particular, I want to consider it over a finite field. FQ. And if I have a, so this is, yeah, there's a lot of details in exactly how you might want to define it, but it's going to be some translated A infinity category over a finite field. And so to that, you can look at its Hall algebra. What's also called derived Hall algebra. This is a derived category. Hall of f of s. And the other thing you could do is look at, kind of make this into a contact manifold. So take S times the real numbers, and the Liouville one form. You can use it to make a contact one form here. That's the contact threefold, or like type. And a threefold, then you can consider knots in it. And in particular, I want to consider Legendre knots, since that's going to be kind of compatible with these things or objects in this category. Here is some Skein algebra of graded Legendre knots, or links. This is just an outline, so say what exactly I mean by all these terms. Which is, so this is an algebra over, say, Q, rational numbers. This would be, write it as Skein times R. And this is an algebra over Q adjoint T, positive and negative powers, and I also invert T minus 1. And yeah, if I specialize here T to some power of Q, the claim is that it will kind of naturally sit as a sub-algebra inside here. So we get Skein algebra. Set T equal to tensor with Q. T equal to Q. Q is this prime power which I used here. Then it's a natural injection into this Hall algebra. So it's not exactly equal to the Hall algebra, but I mean, typically when people talk about the Hall algebra, they pass to some subalgebra anyways, because this is kind of huge. So all the isomorphism classes of objects. Kind of it knows about the essential part of it. Okay, so that's a broad outline what will be happening. And yeah, I'll explain what are exactly these things, how does, and particularly kind of the most interesting, just the existence of kind of having a natural homomorphism here. So even in the case when S is just kind of disk or something, this category only contains a zero object. So this algebra contains kind of only scalars. And this also only contains scalars. So we compute some multipolynomial of Legendre links. And this is still an interesting homomorphism because it will tell you that, you compute some not polynomial, and what this is counting is solutions to some Mark-Cartan equation. Okay. Yeah. So the oval surface. Yes. Yeah, a lot of these things have sort of appeared in this conference, but maybe I'm using sort of slightly different variants of it, but not for the oval domains. So, but just to be precise, so S should be some compact smooth surface with boundary and some level 1 form. So d lambda is a symplectic form.
You look at the mark points. So look at the boundary.
You can also consider mark points on the boundary. That's a good point. We're just forgetting about them right now just for simplicity. Yeah. But you can definitely consider mark points on the boundary. So just a condition kind of near the boundary, if you look at this the will vector field. The one is effectively dual to this one form. It should be pointing outwards along the boundary. This is just a specialization of the general notion of the oval domain for surfaces. Yeah, and also on some grading. Which just a section, choosing some foliation on the surface, a section on the projectivized tangent. And it allows me to talk about graded curves and then to make this a Z-graded category. Okay, so kind of done this, and now I want to explain this step here. So yeah, it's a threefold. So S times R, and has a contact form which is just lambda plus dc. This is coordinate c on here. And the sort of the model case here is the standard contact R3. R3 and it's minus x dy or dx. So Legendre just means that this one form, look at curves where this one form here vanishes, which means basically that integrate this equation, this is supposed to be 0. It means that z, this kind of additional vertical coordinate which I added, should be just the antiderivative of y as a function of x. So if I project the Legendrian curve, its height, its coordinate in this additional factor is almost uniquely determined up to constants. Okay, and I'll make a simple observation here. This is kind of a priori three-dimensional geometry, and something where kind of the Legendre condition is very nice to have, that if I have a Legendre curve immersed, Legendre curve C, then well, it's just any curve. If I project it back to the surface, I can have some maybe cusps or no longer immersed, but it's Legendre, right, then dz. So it cannot have kind of dx vanishing, but dz not. It's an immersed curve. Then the projection to S is also going to be immersed. Still immersed. Which is critical if I want to define gratings and have them be objects in here. So this allows me to, I can define graded Legendre curves. A grading just means a grading of its projection to the surface. Or grading means that the lift of the tangent vectors of the curve to the universal cover of this circle bundle to find the y's. Cover circle bundle projectivization tangent bundle. Base point by grading foliation theta. That's one way of saying what's a grading on a curve. There's the choice argument. Yeah, by sort of arbitrary curves. And that's kind of one reason why there's a version of the not Legendrian version. Kind of, I don't know what to do with that right now. Okay. So, yeah, so on the other hand, you can look at this category. And there's many ways to define it exactly. What I would kind of want, I definitely want kind of immersed curves to be objects in here. But kind of the ultimate thing, really, I also want kind of arbitrary graphs with some local system of chain complexes to be kind of this to be sufficiently generally defined so that these are objects in here. I mean, it's going to be the same category, but just technically what is actually our objects represented. And
So the category is the same.
Yeah, it's equivalent category, but I want a lot of freedom in how I present my objects. Yeah.
If you draw a graph, you quickly say how like resolve it.
Yeah, that's non-trivial problem. I mean, that to say that if you have an arbitrary graph, you can resolve it into kind of just curves that contains the classification of objects of this category, which I proved in my thesis, but it can use this classification. It's not entirely straightforward. But definitely, if I have a graded Legendre link, and by that I mean it should be an embedded disjoint union of S1s in this S cross R, which is Legendre and which has some grading data, gives an object this category. They typically talk about the exact Lagranges of manifolds. The exact structure just means I'm lifting it to this contact guide. And maybe other fact that this will be finite.
Maybe I don't understand. So your graded Legendre link will give an immersed Lagrangian. How do you turn it into an object?
I'm saying this should be sufficiently generally defined so that immersed Lagrangians are objects in it.
Yeah, but typically for most Lagrangian, you specify additional data. Are you allowing yourself to do that, or do you mean Legendre link without additional data? You do allow that.
I actually will want also additional data, but yeah, right now let's not worry about that. The later loops are extension, marketer elements. And then, yeah, so second remark here is that it's finite enough that I can define Hall algebra that it's form finite or locally proper. So look at X. Total dimension, two objects, then their entire X is finite dimensional. Okay, so next thing I want to explain, how is this Hall algebra defined? So this is the, I guess, classically what people look at often is like Hall algebras of abelian categories, and here it's a triangulated category. It was kind of not really clear to people for some time, I think, how to define it, but then Tone was the first to define it and prove it's associative. So how does this work? So let's say C is a triangulated infinity category. Over a finite field. And assume other strong finiteness that we want the X groups between any two objects should be finite dimensional, and then also below a certain range should eventually kind of be zero. So finite dimensional for all k and zero for k, sufficiently small depending on x and y. Yeah, and also, of course, there's a more sophisticated version of the Hall algebra, which work over any field. But yeah, for the point I'm trying to here to make, this will be kind of enough. If you're not over a finite field, it becomes much more technically involved to define this algebra, as we saw in the previous talk. Okay, so these are my assumptions. And then the category is small or whatever, some set of isomorphism classes of objects. And Hall algebra will be algebra over Q with underlying vector space. Which has a basis, the set of isomorphism classes. So finite linear combinations of objects. Okay, and how is multiplication defined? So some basis vector corresponding to some object A, basis vector some object C, and I write A and C because it's kind of triangles of BC. There's some kind of, now explains where the formula comes from, but here there's a product, k bigger than 0 of x, size of x minus k, c to a, to the minus 1 k plus first power. And this product is essentially a finite product because of this condition. And then plus a sum over classes of extensions from C to A, delta, and then here object corresponding to this extension. So cone C, which is by minus 1 to A. Again, this is a finite, just a finite set. It's just everything here is finite. Yeah, so what is this? You can kind of think of this formula as, well, you have two objects, your product is sort of all the different extensions, but you are counting extensions in a homotopically correct way. So we compare this to the notion of group-wide cardinality. So this right-hand side here is the cardinality of some infinity group-wide. So infinity group-wide is essentially the topological space X. A lot of finiteness assumptions on some multiple groups, then I can write down cardinality, which is sum over connected components, x naught and y naught, and then product k bigger than or equal to 1, cardinality of pi k x this point x naught to the -1 to the k power. Right, so here you think that, well, this X1CA, it's really kind of connected components of some topological space, and entire homotopy groups are X minus K. So this is made more precise in Don's paper on solid, but for our purposes, we don't really need to know that there's an infinity group wide of objects. We just can plug this formula. Okay. Okay, so I've defined some product. Yeah, it's a priori not completely clear that this is associative. But how do you prove that? Well, basically, if you have a triple product, it's counting some kind of twisted complexes with 3 steps. So if you have 2 objects, this is like a twisted complex, 2 objects. Delta is an upper triangular deformation of this direct sum. If you have a triple product, you have some 3-term twisted complex, which this is counting.
With like 3-term twisted complex with 1 matrix entry 0, or?
It's just 3 non-zero matrix entries. E1.
Ah, yes, I see.
These are all degree complexes. Yeah, and of course also that if you have a product of any number of elements, the interpretation is that it counts these kind of twisted complexes. In the abelian world, it was kind of, you're saying that you're counting fluctuations. And also it's unitary, just take the isomorphism, take the 0 object, yeah, just plug that in. This will be a unit for this algebra. Okay, so simple example. Say C is just a category of chain complexes over finite field, finite dimensional, and yeah, the point here is kind of it's already a non-commutative algebra, so just call my field F. So E, I take object F multiplied by F shifted by 1. F and F shifted by 1 have some non-trivial extension, which will give me the 0 object. So if you plug that into the formula, it's E, the trivial extension, F plus F shifted by 1. And then plus Q minus 1 times the 0 object, so let's just write it that. And multiply the other way, then since this extension class only goes one way, you're not going to find this. So this will just be q times this trivial extension. I mean, if you look at Hall algebras of abelian categories, the first couple of examples, the simplest categories, it's always commutative, but you're already for very good, it becomes non-commutative. Okay. But what we're interested in is all of this applied to Fukaya categories of surfaces. So the next goal will be recipe. If I start with a Legendre link, graded Legendre link L, in S cross R, to linearize it in some sense, to associate to it a vector, meaning an element in this whole called phi of L. It's an element in the whole algebra of Fukaya category. And kind of a stupid thing you can do is just take its class and get a basis vector. But this will be something like more sophisticated that in general you don't just get the basis vector in the whole algebra. It's many non-zero coefficients. Okay, so how does this work? Yeah, essentially what it will come down to is counting some kind of solutions to some Morikaton equation. Already you kind of see the way the whole product is defined is also counting some. Right? For this to be a twisted complex, it has to satisfy some kind of Morikaton equation. So product is already some interpretation of that one.
So do you allow L to be an arc or
I can, yeah, so I didn't want to talk about it, but you can also include boundary points, and then L can end on these boundary points. In the case when L is just an embedded arc, this map is in fact just a trivial thing, but it will just be the basis vector. Kind of in all other cases will be a little bit more complicated. So if it's embedded loop, then also it's something fairly simple, just a different kind of monodromies you can put on it, and the sum overall of these different. So this is really interesting when L is not an embedded curve in S. It's a projected embedded curve. Okay, so first step here is to look at the roughly like this Chekhov-Eliashberg idea. So if you look at endomorphisms inside the Fukaya category of L, and it will be kind of important that it's not just.
What is that?
Well, L is an object in the Fukaya category.
No, it's not. You know, we immerse the ground in to make it an object or to do something.
No, L is an exact Lagrangian.
No, it's a Legendre link, which when you project as they be immersed.
It will be, I mean,
So what is that?
immersed curves are fine. I think, yeah, immersed curves are still objects in the Fukaya category.
I mean the notation L belongs to
No, but I mean, yeah. When you define this category and you want it to be defined over finite fields, you cannot allow arbitrary Lagrangians. You can only allow those Lagrangians which have a Legendre lived. And
Can you say what is the definition of that endomorphism? Like what homomorphic disk is? What is the basis? What is the differential?
I think the choice of the genre
Yeah.
makes the law conversion.
But what is the basis of that endomorphism space? And what is the
basically I mean, if you have a self-intersection, then you'll have two basis elements. And there's different ways kind of exactly how to realize it. And
So just
the
pick
way,
one.
well, the way in which I do it is kind of a little bit elaborate in the actual paper. I kind of break off the genre into lots of segments and define some explicit infinity structure. But it's not really, yeah. You can choose your favorite.
Put some augmentation, right, to get that also.
Yeah, sure, yeah, that's what I'm asking,
Yeah.
what he's doing.
No, but I mean, this first lecture of Maxim, yes, so it's how to do it for
Yeah.
arbitrary
No, no, one just say that one need augmentations to get an honest object.
Okay.
It's just a, not a kind of, it's a kind of, you know, algebra theory, but linear when we find something.
I think what confused me is you pick one or, so you
Yeah, that's
pick,
better, right?
No, that will be.
you pick extra data to write the anamorphism or do you not?
Well, in practice, well, the way I do it, I don't need to pick any extra data. But the way, one way to do it is kind of perturb L, right? And look at intersection points in the projection of L with its perturbation. This will be a basis
Sorry,
of this guy.
What do you do with the self-intersections of L?
sorry, one issue was this is abstract, right? There's this piece that you disallow the abstract clause, right? When the curve comes back to itself, like it gives it. So if you don't have those, then it's fine. Right?
No, the fact that it lifts to something Legendre takes care of this obstruction. But for example, this sort of guy.
Yeah, that doesn't have.
But it's not obstructed. These two areas are the same. It will just be the zero object in the category. But I mean, if it did have some M0, that would also be fine for the theory. It's not.
But you do not fix an augmentation of Legendre's DGA.
Not yet, no, this will come. This will come, yeah.
Anamorphism shell.
This is just anamorphism. Yeah. But we'll talk about sort of augmentations in the guise of bounding cochains.
If L is like trephoromon, can you say what that algebra is?
I mean, there will be many models of it, but one way to compute it would be to look at self-intersection points. Each self-intersection point, let's assume it's generically projecting, will give you two basis morphisms with degrees determined by the grading on L. Then there will also be two basis morphisms coming kind of from homology of S1. Type identity and its kind of Calabi-Yau dual. And that's it. So, yeah, so I'm assuming kind of that there's some version of the Fukaya category you defined, and you can, and then this makes sense. No, phi of L is going to be a vector. L is a Legendre link. Yeah. L is a graded Legendre link in S times R. This is some A-infinity algebra. Yeah. Wait, but so the fact is, so what?
L is a three-dimensional.
Yeah. The fact that L defines an object in the Fukaya category uses the fact that it does lift to this three-dimensional thing. So yeah, but in fact, I do use this lift in a way because this has, so what's important for me is not just that this is an infinity algebra, but that it is a filtered infinity algebra. And the filtration, at least maybe if this has several components, will depend on my actual choice of lift to the threefold. So filtered infinity algebra means that there's some decreasing filtration. Yeah, it's called, so this is A. There's some decreasing filtration. A is bigger than or equal to lambda. Lambda is a real number. And so filtered infinity algebra should mean that if I look at the higher mk, something in part bigger than or equal to lambda 1, the kind of additive should be contained in A bigger than or equal to lambda 1 plus lambda 2 plus lambda k. Okay, so how is the filtration defined? Essentially by intersection. Take L take its projection, perturb it, look at intersection points.
Okay.
That's one way.
But including self-intersections, or just not including self-intersections?
Not to include intersection between L and the perturbed copy of L. I mean, that's how you define endomorphisms in the kind of category.
So in particular, for unknot, there would be 4 elements of that.
Yeah. So where does the filtration come from? If I have some intersection point P, and this would contribute 2 basis morphisms in here, then kind of what I remember is that in the threefold, these 2 don't intersect. There's some kind of difference in height. So assign some height to basis morphisms. Yeah, and also, I mean, this filtration is, I think, also known in the context of Kernel basis morphisms, which is equal to the difference in the z value of these 2 branches, plus or minus, depending on 2 morphisms, 2 sides, and then a bigger than or equal to lambda will be generated by basis vectors height bigger than or equal to lambda. So, I mean, if the curve is just projects to also an embedded curve, then this filtration is trivial. All the interesting thing comes from different branches crossing on different heights. And this, yeah, in particular, there is some non-negative part of this infinity algebra, which is also an infinity algebra. And this is, I mean, roughly, this is some infinity version of the Chekhov, it's known as Chekhov with the algebra, DGA. And I think it also has some 4-dimensional interpretation. And you can take the contact threefold and then turn it into a symplectic forward, symplectization, again multiplied with R, and think of the Legendre link as some 2-dimensional Lagrangian in there. Okay. So now it's where I set up kind of some Markov equation. So what I kind of, the idea is to look at all the different objects in the category which are supported on this link. So what I mean precisely, so if take this, so now just take the piece that's height bigger than or equal to 0.
So I think in 3-dimensional cases, Chekhov is somehow, this generator has a homology of S1 plus the intersection points. And Chekhov algebra, so now this S1 homology of S1. Which one is your choice in this case in 3 dimensions?
Yes, I do want the homology of S1 to be included. I think maybe they don't include the homology of S1.
Yeah,
Their generators are just intersection points, yeah. That's why I say kind of roughly. So I have some additional. Maybe it's actually more less than or equal to 0 part, or less than 0 part, morally. Yeah. But I think, yeah, if I find one of these intersection points, one of them will be positive height and one morphism be negative height. So taking the non-negative part sort of is taking roughly half of the whole infinity algebra. Okay, so I want to now associate with this some infinity category, which, so objects in here correspond to different choices of bounding cochain. That means object in this MC of L object in this infinity category is Markoton element delta in degree 1 part of A non-negative, and should satisfy the Markoton equation. You might be worried here that also could be potentially infinitely many terms, but if I have some mk and k is big enough, then this includes some disks in the surface which have bigger and bigger area. So this definitely it converges in some sense with respect to this filtration. So this makes sense. And the so this is the kind of general algebraic procedure of twisting a category in delta 1, just the original, all of A not the negative part, and then the infinity structure. I get by twisting the original infinity structure of A, so inserting Markoton elements into the higher products. Twisting. Okay, and this is also goes under the name of augmentation category, and what Schende and collaborators.
So this is really the same thing as that category, or it's roughly the same?
It's really the same. I mean, there's two versions again. I can look at the non-negative part in here, and then that's really the augmentation category. Or I can look at all of A, and then that's corresponds to kind of subcategories of Gaia category. Yeah, and also it's here, it wouldn't really matter if my original infinity algebra had some curvature, because now kind of in this construction of looking at Markoton elements, I get something on this infinity. Yeah, and this is also, again, it's filtered. Because my Markoton elements were in the non-negative part. Okay, yeah, so what I'm trying to do is produce an element in the Hall algebra, and that will just come from counting objects in here. So yeah, I mean, what's really going on? So I took different objects in here. I had my original Legendre link. Different objects in here correspond to, first of all, choosing some monodromy along all the components of that link in my finite field. And then second of all, if I have one of these intersections, to choose some extension class at that intersection point. And the whole thing has to satisfy the Markoton equation.
But you want to produce element of Hall algebra usual Fukaya category, not augmentation category?
Usual Fukaya category. But it was kind of just some push forward. So I have this. So this is some infinity category of finite number of objects, and again, this idea of infinity group-wide cardinality, there's here some kind of uniform measure. Just some element U, MCL, non-negative part, inside some kind of rational linear combination of isomorphism classes. They're counted sort of by their automorphism groups. So this is, by definition, will be very similar to this group-wide isomorphism classes of objects. And take basically their sum, but weighted by the size of their automorphism group in the infinity sense. So that's the automorphism of X. 1 over size of automorphisms of X in the classical sense, and then correction factor coming from negative X's. Okay, bigger than or equal to 1. Size of X minus K of this X. Factor of -1, K plus 1, times basis vector of X. So it's basically just the sum of all my objects, but weighted by their size of their. So, and then, yeah, kind of just the last step. Now I can just push this forward to the whole algebra of the Fukaya category. Here I need to use the fact, or I kind of need to assume that my definition of the Fukaya category is sufficiently general that I know that this sort of object, if I have a solution to this Markov equation, actually gives me an object in the category. I have a functor, this category of Markov elements, L, and 2 by a category. And so then I can push forward from Q linear combinations of isomorphism classes objects here. Also this to all algebra. Chi-S. And I just take this kind of uniform measure, which I define on the left-hand side and map it. This is going to be my phi S. So U. L maps to F lower star of to read by definition this element phi of L, which I want to call up. Okay, so just a quick recap. I have this Legrandian link. I can look at all the possible ways of putting monodromies on it and extension classes at intersection points. And these are solutions to some Markov equation, and then if I know all these solutions, it gives me some vector, some element in the whole algebra. Okay, and the properties that this has is, well, it depends only, first of all, on the isotopic class of the link. L1 isotopic. Family of embeddings of Legrandian links, relating them. Then phi of L1 is phi of L2. Also, there is some compatibility with the product. So, since my contact threefold has this special form that it's a surface times R, I can I have some kind of product operation on links, which is just I have two links, just stack them on top of each other. So, at links L1 and L2, there's a product. L1 stacked on top of L2. Almost canonical. I just need to translate one link to be very big in C coordinate and then take their union. And this product gets taken to just the product in the whole algebra. It's phi of L1 times phi of L2. And roughly speaking, this is very plausible. When I'm taking the product here, I'm counting some extension classes going from L2 to L1. And these correspond to some morphisms in the additional degree 1 elements if I look at the endomorphism algebra of this concatenated L1 stacked on top of L2. Okay, so I've kind of still not really explained what is the Skein algebra. But there's also a point here that you don't really need to know how the Skein algebra is defined. You could just ask yourself, well, so I have some map from linear combinations of isotopy classes of graded Legendre links. And this phi is a linear map to, in fact, algebra homomorphism, doesn't matter, to the whole algebra. And you could ask, what is the kernel of this map? And the answer will be exactly you get, it's generated by Skein relations. And why that? So in higher dimensions where you don't really know what Skein relations are, you can kind of, I think you can produce all the same stuff in for higher dimensional stable domains. And some interesting question, what is this kernel? Here. Kind of by definition. So yeah, this is not yet the Skein algebra, but we pass to the kernel of phi. Since the claim here is generated by some Skein type relations. Which are the following. It's roughly like what we got, but graded Legendre links, there's some slightly different set that's appropriate here. So first one, I switch, I have two, this embedding, and at some point it's kind of one branch is passing through another. So if I have a picture like this, and yeah, there's a question here now of what is the grading of these curves, right? So what's the degree of this morphisms at this intersection point? And let's say the grading of these curves is such that here there's a morphism of degree 1 and of degree 0. So there's a non-trivial extension action form. And then this minus q times the link, but two branches interchanged. Is equal to q minus 1 times with this intersection point resolved. Because the grading is in such a way that these are actually canonically graded curves. And that's the kind of the most important one. Of course, there has to be some relation if these degrees are different, meaning I cannot do this moving. This term kind of falls away. So there's something, let's say here there's morphisms of degree 1 minus n and n. And this is equal to minus q. Minus 1 to the n times the other way, the other crossing. And then finally, there's some normalization for the unknot. So this is, of course, the zero object in the Fukaya category. So it has to be some scalar just with multiple of identity. And that just works out to be 1 over q minus 1.
these
again,
relations already sit in the kernel of the algebra augmentation category, or are some introduced when we have to go into certain?
The augmentation category is something that's kind of defined for, I guess, for a fixed link. Yeah, but it does make sense to combine the links. These will still be, I think these will still be true, yeah, the level of the augmentation category. No, well, I mean, this is not really the zero object in the augmentation category. That's the issue. But I'm really, this push forward here, there's a lot of objects which are not isomorphic over here, but which map to something isomorphic over here. But augmentation is not fully fulfilled. Yeah, so sorry, yeah, this is not, I think I really need to go to the Fukaya category to have these relations. Yeah, and then the claim is also kind of a few. These are not only in the kernel, but the kernel is generated by all of these. And yeah, and also, yeah, there's some, this was mentioned, there's some version where I have boundary points, and then there will be kind of a few more relations that tell me some boundary points. And then in the threefold, there's some kind of line, this boundary point times r, and things should end at a different height of this line. And there's some sort of Skein relations for what happens if I switch. I have two branches coming at projecting over this boundary point, and I switch them around. There's again a few more relations that tell you how to deal with boundary points. Right? And, yeah, the point is here, these relations kind of, they're not really arbitrary, they're really forced upon me by this whole construction of this map phi. Just one last thing, mention some kind of related work here, which sort of inspired this project. So, one is Morton Samuelson, and they look at basically case when this is a two torus. Although so what they really compare is the Homsley PT Skein algebra, so kind of what Vivek defined, of the two torus, and some kind of Hall algebra of dB of the elliptic curve. So they don't talk about the Fukaya category, but kind of by mirror symmetry, it says that there's some relation kind of between Hall algebra of the Fukaya category and Homsley PT algebra of the two torus. But their proof works just by computing generators and relations for both. It doesn't really tell you there should be a relation. Yeah, this is not really a special case yet of what, this is sort of similar kind of statement, but it's not really a special case of what I'm proving, since D2 is not Liouville. And this is not about Legendre anywhere. And then also Cooper Samuelson look at actually Hall algebra of the Fukaya category. And I think they identify some kind of sub-algebra, which is the image of this map, which I'm defining, but in a slightly different way. But yeah, also, they don't talk about Legendre yet. And then work of Rutherford, Schender, Sivak, which, yeah, I think, yes. Actually, this case, although they do something a little bit different, they relate the count of these number of solutions of the Markov equation to something called graded normal rulings of the Legendre norm. But I think if you combine some papers, I think you get you can prove from this theorem which I'm proving in this special case. Okay, so yeah, I'm going to end here. Thanks.
Can you use this isomorphism to say that every spherical object is an embedded circle?
So I don't really get an isomorphism. I just get an inclusion.
Yeah, okay. But suppose you have a spherical object in the die category,
Yeah.
it would probably live in the image of the thing that you're, right?
Roughly, right? So what's really in the image is kind of all the different possible monotonies kind of evened out, averaged out, all the different monotonies, yeah.
So, but is it necessarily an embedded curve? So can an immersed curve with the additional more compound solution be spherical?
I don't think that's possible, but this theorem doesn't really say much about that. This theorem, I mean, there is a classification of objects. Again, this talk doesn't really use anything about classification of objects in this category. You might want to kind of know more exactly what is the image, and that you can describe the image using maybe perhaps the classification of objects.
Do you know, so for the other surfaces, do you know what is the basis of the Skein, you know, the basis of the Skein model? But it's Legendre kind?
Again, this tells you to be some.
No, it's a question about orthogonal to this. I mean, it's about understanding the answer. Do you know?
Sort of. I think one way to get some kind of answer, maybe to also fix some stability condition. Yeah, so there's maybe really quick. Yeah, so you're asking kind of what is the basis of the image of this thing,
Yeah.
the equivalent. And I do, yeah. Right now I don't know kind of some algebraic way of saying what's the image. It just takes the image of this homomorphism. But yeah, that's a good question. Something that I want to look at to give some maybe explicit basis of this.
Other questions? It's mostly the same problem.